This is Kumar Shivendu. I'm a software engineer at Quadrant, which is a vector database. I love search engines, distributed systems, and LLMs. The topic for today is chaos testing, breaking a database on purpose, and this database is Quadrant. Um, and like the topics to cover would be mainly like a bit of intro to vectors and vector search, overview of Quadrant, why we needed chaos testing, and different components of chaos testing, and finally the results that we got. Right. So a bit about vectors. Vectors are mainly like points in an n-dimensional plane in such a way that if 2 points are close to each other, that means like they represent something similar. They could be representing two similar, songs, two similar images. Could be anything. Basic idea is that they compress the meaning, and you can generate vectors from pretty much anything. And generally the popular ways to generate these vectors are this language and vision models, which kind of includes your chat gpt, and this metric learning approach where you kind of can convert any kind of data into vector by specifying the close like positive and negative pairs, right? And one of those like models which is generating using this clip like metric learning approach is this clip model, which kind of understands text and images at the same time. So the same model will kind of understand text and image, generate vectors which are closer to each other if the inputs were kind of representing the same thing, right? So that's about vectors. And vector search in general is this idea that a very good use case of that is like this Google search, reverse image search, where you point it to something and it figures out the relevant like species of the plant or the animal or anything, or the cloth. So yeah, like the general idea is that you humans search for things and not strings, right? And like keyword search by default is kind of limited to like in terms of the things that it can search for, and it cannot directly understand images, audio, video, all these formats. So the general philosophy for vector search is that you kind of try to find nearest points in that dimensional plane, right? And like to optimize this, you can do some kind of indexing and approximation, but this problem is still kind of hard to scale and manage. Like all these vectors, like especially imagine if you have like a billion vectors, and that is exactly where vector databases or vector search engines like Quadrant come into the picture. So Quadrant is like an open source vector search engine with more than 23,000 stars now. Uh, and like it's written in Rust, has SDKs for most of the popular languages like Python, JavaScript, Java, and many of the popular users of Quadrant are Perplexity, X.com, Meesho, Flipkart, and others. So yeah, so a bit about the indexing API, like the way how you insert data is like, you have collections which are like tables, and you put data into cape table, and here the focus is more on the vectors. So you have some point ID, right? And with each point you have some vectors attached to it, and these numbers are kind of generated by the machine learning model based on the understanding of the image, let's say, right? And assume this is like a rentals collection, right? And you can attach some JSON payload to it for further filtering and just general metadata. So now to search, you can do a post request to the same collection, right? And pass it the vector and do some filtering based on certain conditions like price greater than, less than, all these things, and it will return you the relevant points that are matching, and along with some payload, right? So that is like general about vectors, vector search, and vector databases. Now specific to Quadrant, like the general architecture is that you have some SDKs, they talk to Quadrant. Quadrant is like a running in generally like a cluster mode, especially for large scale deployments, so you have multiple nodes. And yeah, like they store all your vectors. And like the format that we have for that is like Quadrant has collections have like shards for data, and shards also have like some segments. And the way we manage like a cluster is like this popular raft consensus algorithm. This manages the state of collection, shards, transfers, all these kind of things. And the actual points are synced with like a slightly different logic. But yeah, that's the general overview of the architecture. So the question is now like why we needed chaos testing, right? So first of all, like there are many moving parts to distributed system. Like first, we just discussed like consensus, all these segments, sharding, storage, wall logs. Like this HNSW index is like a specialized index for vectors. And especially when deployed, you have like even more moving parts like this Kubernetes, right? We have our own custom Kubernetes operator. I will talk about a cluster manager service that we wrote. Uh, that and like failures around disk, backward compatibility, so many things which can kind of go wrong, right? And anything can go wrong, and that's why we should prepare for the worst. And general idea is that we should catch and fix bugs before the users find it, because especially because there's like a database product, so stability and reliability for the product, right, is extremely important. uh, So yeah, and generally it's also that like we have like a lot of tests everywhere throughout the code. We do every kind of possible test that we can, but it's still impossible to write tests for every possible scenario, because with every new feature merge is like a combinatorial explosion, right? So you cannot write tests for every single possible scenario. So that's why we also like need like something like chaos testing, which can embrace some randomness and do some real world testing around continuously, like so it can figure out issues. So yeah, so the general philosophy is that we kind of test quadrant in some of the worst possible scenarios and see how it, if it degrades, and if it degrades, how can we fix it. So yeah, yeah. So why existing solutions were not enough? Mainly because they felt a bit limited for a database use case, while also being bloated. We also need like custom cluster setup, some checks, and like the simplicity of like mm, you know we felt that we could design like a much simpler solution than like the existing bloated solutions, because we need, with the requirements were relatively simple, and we already have tools like BFP in house, which we use to like load test the database. Um, so for the Kotlin cluster, right? So we have a cloud-like environment deployed using Kubernetes. Uh, what it does is basically like we also have like this with every merge into the dev branch. We build and deploy a container to GitHub container registry that is then pulled to the cluster in the Kubernetes cluster, and like we have like a operator there, Kubernetes operator, a cluster manager service that I wrote, and Kotlin cluster, which has like all the pods, like shards, replicas, everything. Like so, so Kotlin cluster is basically like 3 to 5 pods running, each running with like 0.5 CPU, 2 GB of RAM, like, and these are like created by the operator, the pods, and the Kotlin operator, Kubernetes operator plus the cluster manager service together, they kind of allow the cluster to scale, replicate, reshard, and balance the shards. And only Kotlin cluster manager knows about the internals. The way they are designed is like the operator knows about the pods, right? But it doesn't know about the shards and consensus and indexing, all those things. It talks to the cluster manager for this, and sometimes cluster manager also talks to the Kubernetes operator to like drop a pod or something, right? So it's like a two-way communication in that sense. So yeah, so we have like custom tool BFB for the load generation part, and which is like constantly hammering the cluster. It's running like as two different pods in both modes. One is like observability mode, where we are overriding the same 200,000 points at like 100 points per second. The reason for this overriding will be is because we want to test for eventual consistency. We are also searching at like 11 QPS, which is like a million requests a day. And like one example of BFB is like this kind of a CLI thing. So yeah, and as I say, like we thought we could design like a simpler solution. So it's just simple, Kubernetes KTS job cron jobs, right? With combined with kubectl commands to run like custom stuff with Kubernetes, and some bash scripting. If required, you can also do Python. Not very difficult to do with a cron job. So we have like some kills which are like triggered every 5 minutes with some randomness as well. This kind of triggers shard recovery, and whenever like the pod is killed, it should be recovering, and then we expect the data to be consistent and everything over time. So yeah, all that is checked. We scale up and scale down the cluster, like so this kind of adds or removes nodes from the cluster, right? So more pods are created or destroyed, and this triggers like shard movement, because now data has to be rebalanced so that the load is divided between the nodes. And we also take snapshots, which is like kind of slows down the node for a while, and it also occupies disk space, so it does that flow as well. And we have resharding obviously for splitting and merging shards, which also does partial migration of data from one shard to another. So yeah, and for health checks, right, we mainly check for these degradations. Obviously, like the important one is like node and shard should be healthy, readable, and writable. It's a database. It's a critical thing that it should happen despite all the chaos, whatever happens. So vectors and payloads should be consistent between replicas. Again, very important thing. Quadrant is like a eventually consistent database. So we expect eventual consistency, and I will tell you how we do testing for eventual consistency. Points should be present, obviously, and all this happens in the presence of like all these chaos, like rolling updates, snapshots, resharding, node restarts, horizontal scaling, and like 10 other things that we have started like adding over time. So yeah, we kind of persist all these results to Postgres and the logs to Loki. And the testing for eventual consistency happens like this: like you have 3 shards to replication factor. So totally you have like 6 replicas, 3 to 5 nodes. This two replication factor of 200k points is like 1.2 GB of data with vectors, right? And let's say cluster is in like a high load scenario with indexing and IO. So it takes like 2.45 seconds or 2.4 seconds for this comparison internally between the nodes. Uh, so and BAB in the meantime, like it overrides the 100 points, right? So what will happen is like almost 240 points will be overridden in the same duration. So like you can obviously expect that some points will be declared inconsistent, right? So we that's where we kind of retry the same previously inconsistent points for at max like 10 like attempts, and if it is taking any longer than that, that means like replication lag and it should be reported, it should be detected. So yeah, that's there, and like in the next round we like kind of keep on doing this like checks, right? And so that's there, and you can see the dashboard here. So we have like BAB search and upload running, right? It's checking the status of the like containers, and like this data consistency checks. All that data is like kind of stored in Postgres. Your container versions, as you can see, like so many like scale up and down and kills and everything, right? It's very aggressive. Sometimes it even like breaks consensus because you need like three nodes for consensus to work, but cluster kind of still works and revives itself. So it's a very like good thing. So yeah, we take data from Loki, Prometheus, Postgres, and some other sources. So like we monitor uptime, data consistency checks, all the system resources like CPU, RAM, disk, everything. So the results are mainly like we have been able to fix 40 plus like very hard to reproduce like rare bugs. Some of them have been a bit critical more than the others. But yeah, like these bugs were kind of undetected by other parts of the system despite like us testing like different flows. So chaos testing now feels like the production for the coding. Any major kind of release that has to happen, kind of we let it like run through chaos testing for a while before actually like making it like, an actual release. And yeah, and what doesn't kill you makes you stronger. So we have emerged stronger as a product and as a team. So that's great. So summary is like mainly that complex systems can have critical bugs that are reproduced only when like multiple conditions are met, and it's impossible to test for every possible scenario by writing tests because it's a combinatorial explosion. So and chaos testing is all about embracing randomness so that you proactively simulate failures and avoid issues in production with your real customers. So you can find me on Twitter here, and that's my LinkedIn QR code. I hope you enjoyed the talk and learned something from it. Thank you very much. Bye.